let's try to solve this problem here. So there's a horizontal beam in this figure over here and it weighs 150 Newton. So this bar here, this beam here has a weight of 150 Newton and its center of gravity is at its center. So if you see a center of gravity to be at the center, most probably the beam here has an evenly distributed mass. Okay, it's not necessary, but it's usually that case. And in our syllabus, we restrict ourselves to uniform rigid body in which the mass is being distributed evenly across the object. So the center of mass should be at the center of the object. In this case, yes, that is the case. Find the tension in the cable, which is this cable over here. There's a pulling force exerted by the rope on this beam over here. And B, you are asked to find the horizontal and vertical components of the force exerted on the beam at the wall. So this force here is exerted at the wall. At the wall means by the position of the force is at the wall, but it's exerted on the beam. So it's most probably exerted by this structure over here, which we can call it as pivot. It's exerted by the pivot on the beam, and this pivot, because it's positioned at the wall, that's why this force is exerted at the wall, but it's exerted on the beam by the pivot. Okay, so we're interested in the force over here and we're interested in the force happening around here. So how should we solve this problem? Again, we notice that this object here, it's not moving to the left, to the right, up or down. So it's remaining at rest. It's remaining at rest throughout the process. So it's not moving. And in this case, you should know that it follows Newton's first law. At the same time, you see that this beam over here is also not rotating. It's not rotating and it remains not rotating. So in that case, you know that the sum of torque should be equal to 0 as well. So this is a static equilibrium situation. So we'll be analyzing it using sum of torque equals to 0 and sum of F equals to 0. But again, there's some steps you need to follow through in order to solve this problem systematically. So let's try to solve this together. First, we'll start by drawing a free body diagram. For this situation here, there's two objects, the beam and this hanging object over here. But I believe you all know that the object of interest should be the beam over here, because we are interested to find the tension over here and the force over here. So everything here is exerted on the beam. So our beam should be the object of interest. So let's use a line to represent our beam. Okay, so this horizontal line here is representing our beam. So let's try to determine the forces acting on the beam by asking ourselves the 5 questions. The first question, does the object has mass or not? Yes, this object has mass and therefore it has a weight of 150 Newton. So in that case, we should draw the weight coming out from the center of gravity. In this case, weight should be coming out from the center. Okay, so this is the first force. The second question is whether this object here is attached to any strings, ropes or cable. Well, you see there's 2 strings attached to it. That means you should expect there's 2 tension involved in this free body diagram. The first tension will be this tension over here. So let's draw tension. The tension should be away from the object along the rope. So in this case, it should be tension 1. And of course, we have another tension, which is holded by this hanging object over here. So this tension here, let's call it T2. Okay, so when we are drawing free body diagram, if the angle we are able to obtain it, then probably it's good that we obtain the angle as well. So we know that for this situation here, tangent theta will be equals to opposite divided by adjacent for our theta over here. So in this case, we know that it will be 3.00 divided by 4.00. And if you proceed to do your inverse tangent, I believe you should get an angle of 36.87 degree. So this is the angle over here. Okay, it's between the object and the tangent 1. Okay, so we have asked ourselves the second question. We have determined all the tension. Next, we move on to the third question to see whether this system here has any force being explicitly mentioned in the question or being labeled explicitly in the diagram. In this case, they didn't mention any kind of specific forces exerted by some other stuff, so there will be no external force. As you look at the diagram, there's also no kind of force being indicated here, so there should not be any external force. Fourth question, we see whether there's any rough surface relevant to this situation over here. Well, if you look at the beam over here, the beam is in contact with the pivot, so in contact with pivot will be reaction force. But another end is in contact with 2 strings, so that will be tension. So friction is irrelevant in this situation over here. So let's move on to the fifth question to ask ourselves whether the object is in contact with anything or not. If it's in contact with something like a flat surface, then probably there's normal force. But if it's attached to something like a pivot or a hinge, then there should be reaction force. So in this case over here, we can see that the beam is attached to the pivot over here. So since it's attached to a pivot, you should expect there's a reaction force over here. So how do we determine the direction of reaction force? Again, you can replace the pivot over here with your hand. So if this is your beam, right, you replace the pivot here with your hand holding the beam. So now try to imagine how will the beam exert a force on you. Well, the beam is now poking into the wall while being supported by the pivot like this. So you should expect the beam here to be pressing on your hand while at the same time poking into your hand also. Both of these should happen together, right? Because yeah, it's basically you hold a string like this, you're holding it, you're pulling it. So to make sure it's horizontal, you have to push on the wall in order to remain horizontal. If it's not pushing on the wall, then you go through the wall like this already. Okay, so it's definitely pushing on the wall, while at the same time it's not sliding down. If it's not sliding down, that means it must be supported by something. So you should expect it to press on the pivot while pushing into the pivot. So in that case, your pivot should exert a force which is trying to prevent it from going inside. So you should have a force pointing this way, and the pivot should also has a force exerted on the beam to prevent it from falling. So in that case, you should expect a force upwards. So you have a force pointing to the right, and you have a force pointing upwards. So the combined reaction force should be pointing this way. Okay, but I believe this is too difficult to understand, so here I draw another diagram in order to show you a different way of determining the direction of reaction force. So over here you see a diagram which I replicate from the diagram in the book. So over here I use this blue color thing to represent the hinge or the pivot. Okay, so another way of me determining the direction of reaction force, right, what I do is I assume suddenly I remove the pivot from the picture. So if I remove the pivot from a picture, definitely this bar will move, right? Because previously the bar is supported by the pivot, therefore it's not moving. Now if I remove the pivot, what will happen is the bar will be moving. So let's try to think how the bar will be moving once the pivot is gone. Okay, I'll use this brown color bar to represent how the bar moves when the pivot is gone. Well, you should expect this end of the bar should be falling, while this end of the bar probably falling not so fast because there's a rope hanging onto it. So you should expect it to swing downwards. At the same time, because this is a string, you should expect the whole object to swing downwards like this as well. So something like this. Okay, you should expect this end of the object to be falling, while this whole body here is also moving towards the left. So if that's the case, right, you should be observing that this object here is moving downwards, and this object also should be moving to the left at the same time. Okay, so the pivot is there to prevent that from happening. So if you want to prevent object from falling, you need to have a force that is pointing in the opposite direction. So you should expect there's a reaction force in this direction in order to prevent the bar from falling. At the same time, you see that this whole object here will be moving to the left without the pivot. So the pivot is there to provide a force pointing to the right in order to prevent the whole beam from going to the left. It's there to prevent the beam from going to the left, so the force must be exerted in the opposite direction. So therefore, you should expect the reaction force to be pointing in this direction. So that's how I imagine, or that's how I determine the direction of reaction force. I imagine the hinge disappear, then I see how the object will move. If the object is moving downwards, then you know the pivot is actually exerting a force upwards to prevent it from falling. If you see the object will be swinging to the left, then you know the pivot must be exerting a force to the right to prevent it from swinging to the left. So you determine how the object moves without a pivot, then you know the force will be opposite the direction of how it will move without the pivot. So this is how I will determine the direction of reaction force, and from there I know that the direction of reaction force should be something like that. Okay, here's a note, right? Direction of reaction force, you can't be 100% sure of the direction of reaction force just by using this kind of method of determining it. Again, once you determine this, this is just using your logical intuition in order to determine the direction. Later, when you proceed to your calculation, right, when you see that your RY is negative answer, then that means your prediction is wrong. You have to flip the direction. The most accurate way to determine the direction of reaction force is based on calculation, but you can use logical intuition to predict the direction before the calculation. And what we do now is just predicting the direction of reaction force. To make sure it's correct or not, we still have to go back to calculation, which we will find later, the horizontal and vertical components. So let's try to draw our let's try to finish our free body diagram by putting in the reaction force. So we should expect reaction force like this, and this will be our complete free body diagram for this situation over here. Okay, so once we have done step 1, let's clear up some of stuff because I don't have that much space later. So we have finished step 1 by drawing the free body diagram. What I will do now is I will proceed to step 2. Okay, step 2 will be to do tick at or crosses for all the forces that are in the free body diagram now. Again, we tick beside the force if we know the value of force. We cross beside the force if we don't know the value of the force. So let's scan it one by one. Reaction force, we have no idea what's the reaction force over here. At this point over here, you have no idea. So because you have no idea what's the value for reaction force at this point, you know that you can put a cross beside the reaction force. Next, for weight over here, it's mentioned that the weight is 150 Newton. So you know that you will have the value for this weight over here. Next, for this tension 1 over here, you are asked to find tension 1. Tension 1 is question A. So because you don't know a tension, you put a cross beside your tension. And for tension 2 over here, you should be able to know the tension because you know the weight of this hanging object is 300 Newton. So how are you supposed to know the tension for tension 2 over here? What you can do is you should draw a free body diagram for this hanging object over here. So I'll call this a hanging object. I will draw a free body diagram for this hanging object over here. So we have the dot representing the hanging object, and this is the axis. You know that this object has mass. This object here has mass, therefore it must have weight. Okay, so let's call it weight of the object, okay, to differentiate it from the weight over here. Okay, then next you know that here there should be a tension pulling upwards because this is a rope over here. So this tension here, you know it's supposed to be equals to the tension 2 over here because they share the same portion of the rope here. So the T2 over here should have the same T2 as the T2 in the free body diagram of the hanging object. So these two should be the same. And at the same time, you know that this hanging object here is not moving because this hanging object here is at rest and remain at rest. Therefore, you know that sum of Fy for the object will be equals to 0. And therefore, T2 minus weight of object will be equals to 0. Therefore, T2 will be equals to the weight of the object. Therefore, T2 will be equals to 300 Newton. Therefore, you know that T2 here will be having a magnitude of 300 Newton. And due to that reason, you are able to say that you know the value for T2. You can't straight away substitute because if this object is accelerating downwards, then T2 is not equals to W of the object. T2 is not equals to the weight of the object if the object is falling with an acceleration or rising with an acceleration. So it's always important to do your first law or second law for this situation to see what is the tension equals to. Okay, but in this case, because the object is not falling, not rising with an acceleration, therefore, you know that T2 will be equals to the weight of the object, and therefore, you know that this T2 over here has a value of 300 Newton in terms of magnitude. Okay, slightly little detail that you need to be a bit careful of. Okay, so now we have determined the ticks and crosses already. We have done with step 2. Let's move on to step 3, in which we pick our axis of rotation. How do we pick our axis of rotation? We scan across the whole object, looking for a point which has the most information that we don't know. So we look for a point which has a lot of crosses. Well, if you scan over the whole object over here, I believe you'll only see 2 points which have crosses. First is the left end of the beam, second is the right hand end of the beam. So these 2 points are good candidate for our axis rotation, but which point should we pick as our axis rotation? Again, we pick the point which has an unknown that we are not really interested in. Well, in this question over here, they ask for tension and they ask for horizontal and vertical components of the force. So actually, both of these we are interested to find the value. So technically, both of them are interested. But if we solve it step by step, then we should start with solving the tension, right? That means we are more interested with the tension right now because that's question A. We are less interested with the reaction force over here. So we should put our axis of rotation at the point which has unknown that we are currently not interested in. So because of that, we will pick this point over here as our axis of rotation. Okay, so once we have determined our axis of rotation, right, what should we do now is we should write it down. We pick the left end of the beam as axis of rotation. And once left end of the beam as axis of rotation. Okay, and once you have determined the axis of rotation, right, you should do an important step. What you should do now is you should determine the distance for all the forces from the axis of rotation. What do I mean is you should do something like this. You should try to determine the distance over here. You should determine the distance of the forces from the axis of rotation. Now only the free body diagram will be complete if you label the distance. It is incomplete without the distance. You need to put in the distance. So for here, we know that this is half of the beam. So half of the beam will be 2 meters. So we can put 2 meters over here. Then we know that from here to here, this is the whole length of the beam. So whole length of the beam, you should expect it to be 4 meters. And with that being labeled, only you can call this to be a complete free body diagram, because it should show all the forces being exerted on the object, and it should show the distance of each of the forces from the axis of rotation. And with that said, this free body diagram is now complete. Okay, so once we have picked our axis of rotation already, we should proceed to do our table, and our table should have 5 columns for the x and y component of force, plus and minus, positive or negative torque, distance from the axis of rotation, and the perpendicular component of the force. So let's try to construct that table right now. So we have 4 forces over here, so I'll put all 4 forces inside here. You have your R, you have your weight, you have your tension 1, and you have your tension 2. So for this situation, you need to determine Fx, you need to determine Fy, you need to determine plus minus, you need to determine R, and you need to determine the perpendicular component of the force. Okay, it's perpendicular to the R over here. Okay, so let's go through it step by step. So for the reaction force over here, the reaction force is over here. So the X component will be resolving this one. Okay, we'll be resolving this to its X component. So this will be Rx, then this will be Ry. So your Rx here is pointing in the positive direction. So you can label this to be, for your Fx, you can write as positive Rx, because you say it's pointing in a positive direction. To the right is positive. So Ry here is pointing upwards. Upwards is considered a positive Y direction. So for your Fy, you should say it's positive Ry. Okay, next we look at weight. Weight over here has no X component, so X component should be 0. But for the y component is pointing downwards, so you should lead with a negative first. And now you see that this weight over here is 150 Newton. Only you put in the 150 Newton. Be very careful of the direction. If it's pointing downwards, introduce a negative sign before this. Okay, so now for tension 1, tension over 1 is over here. For this situation, we need to resolve it. So if we resolve it, then you get tension 1x pointing here. Then you have tension 1y over here. Okay, so tension 1x over here is pointing to the left. So you should lead with a negative sign first. It's pointing to the left, so lead with a negative sign. Then after that, you know that this one can be obtained using T1 cos theta. Whereas for Fy is pointing upwards, so lead with a positive first. Then you know that this one is T1 sine theta. Okay, you just fill in the blank. Of course, you can put in the theta as 36.87, but I just write theta, it's fine. No matter you want to sub in now or you want to sub in later, it's fine. Okay, so let's move on to T2. T2 has no x component, so it's 0 over here. Whereas for Fy it's everything. T2, the whole thing is in the y component, but it's pointing downwards, so you should lead with a negative. Then you know that the value for T2 is 300 Newton, so it's negative 300 Newton. So that's how we determine the Fx and Fy. Next, we move on to positive or negative torque. Again, bring out your pen, pivot the position. The axis of rotation is at the left end, right? So we pivot the left end. Then what we do is we check each of the forces, whether they generate a positive torque or a negative torque. Let's start with the reaction force over here. The reaction force is exerted on the axis of rotation. You are pushing the axis of rotation. You are pushing the beam at the axis of rotation. So you shouldn't expect it to turn, because any force being exerted on the axis of rotation will not cause any turning effect. Okay, in that case, we can say the torque generated by the reaction force will be 0. Okay, next we move on to the weight. For weight, the weight is pointing downwards. So if your beam is pivoted at the left end and you have a force pointing downwards, it will cause the object to rotate this way. So rotate this way, it's clockwise. So clockwise should be a negative torque. So this should be a negative torque. Next, for tension 1. Tension 1 is pointing this way with an angle. So if you lock your pivot this way, then you push tension 1 in this direction, you should see that this object here will rotate anti-clockwise. Push is like this. You lock this place, you push like this, you see the object is rotating anti-clockwise. So anti-clockwise is a positive torque. So this is a positive torque. Next, for T2, T2 is pointing downwards. If you lock your pivot like this, then you put T2 pointing downwards, you see that it will cause the object to rotate clockwise. Clockwise is negative, so this is a negative torque. Okay, so this is how we determine plus and minus. Next, we move on to the fourth column, in which we try to determine the distance from the axis of rotation. Well, for R is directly exerted on the axis of rotation, so the distance should be 0. Whereas for weight has a distance of 2 meters away from the axis of rotation. We are measuring a distance between the axis of rotation and the position in which the weight is being exerted. So here the distance over here is 2 meters. So we write 2 meters. Again, there should be no positive or negative for R and F. We just write in the value. So T1 over here, what is its distance? So T1, the force is exerted at this point over here. It's 4 meters away from the axis of rotation. So that's what you should write, 4 meters. And for T2, it's also 4 meters because it's exerted at the same point as T1. Both of them are exerted at this point, and this point is 4 meters away from the axis of rotation. Lastly, we move on to the perpendicular component of the force. We look at each of them one by one. For the reaction force, you have to find the component of force that is perpendicular to the R vector. but r here is 0. If your r is 0, how do you find the perpendicular to r? Okay, if your r is 0, there's no vector for r, so you cannot find the perpendicular component. You cannot find the component of force that is perpendicular to r because there's no r for reaction force. Okay, let's move on to weight. For weight over here, you can see that the position vector will be coming out from the axis of rotation towards the weight over here. You should not draw this in a free body diagram. I'm just showing you how to see where is the position vector. The position vector, it's a line, it's a vector that connects the axis of rotation to the point in which the force is being exerted. So what I draw with the light blue line over here is the position vector for r. Okay, so you want to find the force, the weight, the component of weight that is perpendicular to this vector r over here. Okay, let me just label this just in case you get confused. This is the r for weight. This is the position vector for weight. So the component of weight that is perpendicular to this vector r is the whole weight itself, because the whole thing here is 90 degrees. So the whole thing here should be 150 Newton. So put here 150 Newton. Don't need to care about the sign because you already taken care of the sign in the third column already. Here you just write in the magnitude only. No positive, no negative, just write in the value only. So the whole weight over here, it's perpendicular to the position vector r. So therefore we put the whole value for weight over here. Next, we move on to look at T1. So T1 over here, the position vector will be the vector connecting the axis of rotation to T2 over here. So it's also a vector that is pointing to the right. And now you want the component of T1 that is perpendicular to the vector r over here. So the component of T1 that is perpendicular to the vector r should be the y component. The x component is opposite in direction. It's parallel to the position vector. So this component is irrelevant. We want a component that is perpendicular to the vector r. Okay, so T1y is relevant. So T1y is relevant. We know T1y is T1 sine theta. So you can write here T1 sine theta. Lastly, you move on to look at T2. For T2, you know that r will be again pointing to the right. So T2 here, the whole T2 here is perpendicular to the position vector r. R is pointing to the right, so T2 is pointing down. It's totally perpendicular. So the whole thing for T2 here is the F perpendicular. So we can write down T2 over here. So T2 is 300 Newton. Again, we ignore the negative sign, the positive sign, just bring in the magnitude. Okay, so with that said, we have completed the table. And once we have completed the table, we are done with step 4. Now we are done with step 4, let's move on to step 5. We can start to solve a problem by using sum of torque equals to 0. So let's write it down. Sum of torque is equals to 0. So what makes up this sum of torque? What makes up this sum of torque is the torque produced by the reaction force, torque produced by weight, torque produced by T1, and torque produced by T2. But you know that torque produced by reaction force is 0 because it doesn't produce any reaction force due to R equals to 0. So in that case, you say that the sum of torque is made out of torque of weight, torque of T1, and torque of T2. So let's write all these things here. So torque of weight and torque of T1 and torque of T2 together will create our sum of torque. Okay, sum of torque here can be broken down into these three components, these three torque over here. So whether they should add together or they should minus, it depends on the direction of the torque. So the direction of the torque, we have actually determined it over here already. So what we do is we just use the sign over here and just bring it in. So negative for weight, positive for T1, negative for T2. Okay, that's why the table is important, because once you have done your table, everything just follow the table. Okay, so once you have done that already, your next line should be to do substitution, which is step 6 over here. So substitution, what you do is you copy it row by row. So what do I mean by copy row by row? You start with the first row, then you multiply everything together. So it will be negative 2.00 150 Newton. Okay, then next line, plus 4.00 tension 1 sine theta. So plus 4.00 tension 1 we don't know, we leave it as tension 1, but sine theta, the theta we know is 36.87 degree. This is what we know from up here. Okay, then next line, okay, I'm going to continue below. So next line will be negative this whole thing over here. So negative 4.00 times 300 Newton. And all these things should be equals to 0. And now if you look at the situation here, there's only one tension 1, which is the unknown. The rest of the value is already determined. So for this situation, we should be able to obtain T1 using calculator. You should be able to obtain 625 Newton for tension 1. So tension 1 over here has a magnitude of 625 Newton. And with that, we have managed to successfully answer question A. Okay, now if we move on to question B asks for the horizontal and vertical components of the force exerted on the beam at the wall. Okay, so to solve this problem, we have to look at Rx and Ry. So there are more unknowns over here. So if we have more unknowns, we move on to the last step to proceed to use sum of force in the X component and sum of force in the Y component equals 0. So I'm a bit out of space here. So what I will do is I'll come back with a bit more space. Probably I'll remove this. Okay. Now let's proceed to do our sum of fx equals to 0. So sum of fx equals to 0 because the object is not moving to the left, not moving to the right with a changing velocity. It's at rest and it remains at rest in the x dimension. Therefore, sum of fx equals to 0. So sum of fx should be to sum up everything in this column over here. This is what we have determined earlier. So we can just copy it here. Rx plus 0 minus T1 cos theta minus plus 0. This one I don't need to write it. Okay. So from here, you know that Rx will be equals to T1 cos theta. You know T1 has a value of 625. You know cos theta is just 36.87 degree. So if you calculate everything, I believe Rx should obtain an answer of 500 Newton. So that is Rx, and because you obtain a positive answer for Rx, that means your prediction of the direction in the X component is correct. You predict Rx is pointing to the right, and you obtain a positive answer over here. That means your prediction that it's pointing to the right is correct. Now let's move on to Ry, the Y component of reaction force. So for Y component of reaction force, it's sum of Fy equals to 0. So copy everything here. You have Ry minus 150 plus, okay, I'll straight away do substitution because I'm running out of space. 625 sine 36.87. Okay, this is the substitution, then minus 300 equals to 0. So if you perform your calculation, there's only one unknown over here, which is Ry. So you can perform all the calculations smoothly, and I believe you should get an answer of 75 Newton. Okay, so again, you obtain a positive answer over here. That means what you predict for the Y component, for the direction of Y component of reaction force is correct. It is indeed pointing outwards. So if you want to finalize, Rx is indeed pointing to the right, Ry is indeed pointing upwards. So the horizontal and the vertical components of the force exerted on the beam at the wall has been determined to be 500 Newton for the horizontal component, 75 Newton for the vertical components. So by going through the 8 steps slowly and systematically, you should be able to obtain all the answers required by the question. So this is how you solve a problem involving equilibrium of a uniform rigid body.